Okay, well, let's go and get going. So remember, we have our last quiz and our last problem set due on Friday. So hopefully we cover the material for the problem set today, okay? I do also want to mention to you that course surveys are going to be done online just like they were last semester. So there is now an active link in Canvas BC 403 section that says course survey. I would really like it if you would fill those out. Okay, it's actually very helpful to me. There have been lots of suggestions that have been made in the past by students that I incorporate into my classes. So don't think that I don't read those and that no one looks at those. Those are actually very important, especially for myself. There's always ways to improve. So if you think of something that in terms of ways to improve and that kind of thing for this class, then I would love to hear it, okay? So please do that, okay? And I'll remind you again on Friday. Yeah?
When are the review session sheets due? When do we turn those in?
Oh yeah, so go ahead and turn those review session sheets into your TA at your last review session. If you can't attend the last review session, go ahead and give it to me. So I would like those before the final so I can start to calculate the extra credit for those. Yeah, thank you. Yeah.
Is there a review session this Sunday?
I believe, yes, I believe that Ben is going to give one. I will ask him. I'm fairly certain that he was going to give one. He hasn't let me know that he hasn't or is not going to, but I think he is, yeah. So, okay? All right. Okay, other questions? No? Okay, so let's go ahead and get started. So what is so delicate that saying its name breaks it? Silence, very good. Yes, very good, silence. Some of you didn't want to break it. That's what the deal was. So, okay. All right, so we are now in the middle of amino acid metabolism. So last time we looked at how amino acids get into the small intestine from the lumen of the intestine, just like the carbohydrates. They then will dump into the portal vein, and the portal vein is going to deliver all those amino acids to the liver, and we're going to see today how important the liver is going to be in terms of filtering the blood, in particular of the ammonium cation. Those small intestine cells, they get about 70% of their energy needs from glutamine or glutamate, okay, but they use a lot of these two amino acids to satisfy their energy needs. With glutamine, they, just as a reminder, they use this enzyme glutaminase, which will deaminate the side chain of glutamine, okay, and make glutamate from it. That makes an ammonium cation that's going to get into the bloodstream, okay. The glutamate then goes through these aminotransferase reactions or transamination reactions, and all aminotransferases use glutamate and alpha-ketoglutarate as their substrate or product, and then some are other alpha-keto acid making some amino acid or some alpha-keto acid from some amino acids in glutamate. Okay, so we're going to run into a couple of these today, but the glutamate, once it's converted to alpha-ketoglutarate, it'll actually use pyruvate and make alanine in these cells. Okay, that's shown right here. That then alpha-ketoglutarate will be used as a citric acid cycle to make to provide the ATP needed for the small intestine cells. Okay, right. So what that brings us to is then this slide. Okay, and we have now blood from the small intestine that is delivered to the liver through this portal vein. Okay. And that blood then is going to make its way through the liver until it finally gets to the central vein. And once it gets to the central vein, it will be everything left, the contents left will be delivered to the rest of the body. Okay, so blood that's coming into this vein here, the portal vein, the content of that, there's lots of it, lots of content in that blood. But for our purposes, we need to understand that there is a significant amount of the ammonium cation in that blood. In fact, the concentration of the ammonium cation is about 1 millimolar in blood in the portal vein. that concentration of the ammonium cation, if it were to make it through the liver into that central vein and then delivered to the systemic system, would kill you and I. It would be toxic in very rapid fashion. So it's very important that these cells in the liver filter that ammonium cation out of the blood. And that's what we're going to be concentrating our efforts on looking today. Okay, now, of course, other contents, there will be other amino acids, okay, enriched specifically in alanine, because there's been a lot of the aminotransferase reaction of glutamate to alpha-ketoglutarate, pyruvate to alanine. So alanine will be dumped into the portal vein, and alanine will make it into this bloodstream, or into the blood as well. And then, generally speaking, stuff. Okay, other stuff. Not the least of which would be carbohydrates, okay, that are coming, of course, from the small intestine. We don't care about stuff today. We care about the amino acids, and we care about the ammonium cation. Okay? Now, the other aspect of this, and I'm going to go ahead and just briefly mention this, okay, there is hepatic arteries that will feed into the liver as well. These will be carrying content from the systemic system, the other tissues in your body, skeletal muscle and these kind of things. The content of that, right, so this is the content of that. The content of this, at least for our purposes, what we would care about for today would be glutamine, the amino acid glutamine, and alanine. So if you were to take blood from your arm right now, tap a vein in your arm, tap an artery in your arm, okay, and take that blood, you would find out that of all the amino acids that are in it, the majority of them are either glutamine or alanine. Okay, so those two amino acids are excreted by the majority of tissues. Glutamine in particular, because it carries nitrogen. It's a safe way of carrying nitrogen in our bloodstream. Okay, and we'll talk about, hopefully on Friday, why glutamine is so important and alanine are so important and why they make that. Okay, but that would be the content of this. Both of those are going to then enter into the liver, okay, and these different cell types will then start to filter that blood. Okay, so if we look here, there are actually two cell types that we're going to mention. Okay, we have here the periportal cells, and what we're going to say about these is they have a high capacity for the ammonium cation. And by capacity, I mean they have a large number of the enzymes they need to essentially effectively make urea from the ammonium cation. Okay, there's a lot of urea cycle enzymes in these cells. Higher concentration of those enzymes than are seen in any other tissue, okay, in the periportal cell. Right. After that, these cells would be the perivenous cells. Peri means close, by the way, so periportal, close to the portal vein, perivenous meaning close to the central vein. Okay? These have a high affinity, not necessarily a high capacity, but a high affinity for the ammonium cation. Okay? So that by the time blood makes it to here, the content of this blood ready to be delivered to the rest of the body, there would still be some of the ammonium cation, but the concentration is like 0.02 millimolar. So massive amounts of the ammonium cation have been absorbed and dealt with by these cells. Okay? I wrote up there, it didn't appear. Let's see if I can't get it. Oh, that's not good. Oh, crap. Okay, here's what we'll do. I don't have time for this. We can't mess around today. So, just a second. So the Rockies got slaughtered by the Giants last night, just so you know. They're on the win every other game plan right now, and if they keep doing that, then they won't make the playoffs. So they need a professor in baseball to tell them these things. Okay, there we go. Okay, so now I'm locked behind here. Okay, so contents, ammonium, okay, cation 0.2 millimolar. Okay. All right. Now, the other contents of this would be amino acids. I mean, there would be a selection of most of the amino acids, but in particular, this would be enriched in branched chain amino acid. And by branched chain amino acids, we mean isoleucine, leucine, and valine. Okay. The cells in our liver don't have the capacity to catabolize branched chain amino acids. And so those go right through the liver and end up at the same concentration that you would find them in the portal vein. They end up in the same concentration in the central vein. Okay, and then they're delivered to the rest of the tissues. There are some, bodybuilder types that think that they need more branched chain amino acids in their diet because that's how those amino acids will get delivered, in theory, in a greater amount to the muscle than the other amino acids. So I've never really seriously looked into that, but I've heard that if you've heard that. Okay, that would be the theory. Okay, and then the other contents of this would be more stuff. Okay, all right, and we'll just leave it at that. So the main point here that we want to look at is that these cells, periportal and perivenous cells, have a large capacity and affinity for the ammonium cation so that it really is reduced in this process. Okay, and then again, amino acids will be used by these cells as well. Okay, now I don't want to give you like the full detailed description of how all amino acids are catabolized within a cell, but I do want to give you some exposure to this, right? There are 20 amino acids, and so amino acid catabolism in particular can be really complex. This slide, I think, does a pretty nice job of showing you what each amino acid will be broken down into, okay? Don't worry about the terms glucogenic and ketogenic yet. We'll talk about those hopefully on Friday. But you can start to look at this and you see that these amino acids are going to feed into intermediates that you are familiar with. Okay, for instance, these amino acids can make acetyl-CoA, which is part of the ketone body synthesis pathway. That can then be broken down into acetyl-CoA. Okay, many amino acids will feed directly into pyruvate, many directly into acetyl-CoA, some into oxaloacetate, some into fumarate, some into succinyl-CoA, some into alpha-ketoglutarate. Right. So these are all things that we have talked about in this class. Now, the liver will take those amino acids during a fed state, and it will break them down, many of them, to acetyl-CoA. That acetyl-CoA will be converted to citrate. Citrate in the liver cell will be taken and converted to, as we've just discussed, free fatty acids that will be converted to triacylglycerides, as we discussed, and then to VLDLs. And then the liver will put that into the bloodstream. So that will be some of the quote-unquote stuff that makes it into the blood that's going to go to the central vein, okay, the VLDLs. Okay, some of these amino acids are going to be converted to pyruvate or succinyl-CoA or alpha-ketoglutarate or fumarate, and they will then feed into, in all cases, oxaloacetate. Oxaloacetate can be converted to glucose. Glucose during a fed state will be converted to glycogen and stored for a rainy day, when you go into a fasted state. So that's some of what the liver is going to do to some of these amino acids. Now, let me give you a little bit more exposure here, okay? And let's just look at one particular amino acid, tryptophan. Okay, and you can see tryptophan appears in several different portions of this. The reason is because it's a pretty complex amino acid. So let's go here, and let me zoom in here. Okay, so first of all, one of the things that will happen to the amino acid tryptophan, like I said, I don't want to give you all the gory details of this, but tryptophan, through a 4-step process, we will leave those enzymes unnamed. You can thank me later for leaving them unnamed. But 4 steps to simply break this off, making alanine. That alanine then will undergo an aminotransferase reaction to become pyruvate. Glutamate will be made in that process. Okay. That's essentially, right, the alpha carbon, the alpha amino group, and the alpha carboxyl group of tryptophan. If you want to look at the ring system of this, okay, so there we go. So here's tryptophan's ring. Okay, break this off. That's going to take 9 steps, unnamed enzymes. You're welcome. It'll get to this thing, alpha keto adipate, that thing. And then, I said it one time right, but I didn't do it there. Take another step, and then another 4 steps, and finally become acetyl-CoA, and finally to here. So that's a total of 15 different enzymes that will finally get it into an intermediate that you and I have looked at, acetyl-CoA. That's tryptophan, pretty complex, okay? But we have the capacity to catabolize that. Certainly the liver will do some of that, okay, with these amino acids that are derived from your diet, okay? There's others on here. You can look at this on your own time, though, okay? I'm not going to look at it right now. Okay, so let's come to this slide, all right? So you get this idea, okay, so amino acids are going into these cells. The ammonium cation is coming into these cells. What's going to happen to those? We looked a little bit at what happens to the amino acids here, okay? Now, I guess let me do one more thing here, okay, just to kind of show you this. Again, not naming enzymes here, okay, but if we were to look at serine, it can go in this direction to pyruvate. That'll make the ammonium cation. Okay, threonine can go in this direction. Okay, it can become glycine, and glycine can become carbon dioxide and the ammonium cation. Right. So in many cases, the ammonium cation will be made as amino acids are catabolized. In some cases, glutamine will be made, not glutamine, but glutamate will be made in aminotransferase reactions. Okay. Now, the reason I'm mentioning all this is because we need to trace where that nitrogen's going and where it is all going to land. Okay, so at this point in time, as amino acids are catabolized, it's either going to directly as the ammonium cation or to glutamate. Okay? Right now, when we get to this then, let's go here. Okay? And then we're going to spend some time on this, try and develop something. This is a really, really simple slide. And it's showing a very obviously simplistic view of what we would call the periportal and perivenous cells. So I'm going to go ahead and put a line right here. Everything to the left of that line is a periportal cell. That's what we're going to spend our time thinking about today, and maybe a little bit of the perivenous cell. Okay. And as we look at this, what I want to do is I want to talk about, first of all, we're going to trace the sources of the ammonium cation, and there are 5 of them. And we're also going to trace the fate of glutamate. Not glutamine, but glutamate. GLU. Okay? And we'll start with tracing the sources of the ammonium cation. Okay? What we have up here, this would be the bloodstream. Okay? Coming from the small intestine, so that would be the periportal. Okay? In that blood, as I've already mentioned, there will be the ammonium cation that's going to go into these cells. Okay? So fate number 1, or source number 1 of the ammonium cation entering these cells is blood. And it's really actually, let's just say blood. And there are two main sources in the blood of the ammonium cation. One of them is going to be the glutaminase reaction. And you say, ah, yes, the glutaminase reaction. What is that? Remind me, because you act like I should know that. Glutaminase is the enzyme that deaminates glutamine in the small intestine to glutamate. It's the very first thing that I talked about today. Come back here, 4 slides, right here, glutaminase. Okay, it makes this. Okay, small intestine needs to get energy. It uses glutamine to do that. That's one of the sources of the ammonium cation entering into these periportal cells. Okay. The other, and this is, I haven't mentioned this, would be prokaryotes. Something that we have not even mentioned in this class, and that we should appreciate this. There are more prokaryotic cells in our body than there are eukaryotic cells, by a very large amount, actually, living in a symbiotic relationship. Okay, those prokaryotic cells that are found in our gut metabolize amino acids, but they do not have a urea cycle, and so when they metabolize amino acids, they produce the ammonium cation. You and I absorb that, right, through our small intestine or large intestine, and that then gets into our bloodstream and it goes into these periportal cells. In fact, the majority of the ammonium cation comes from those creatures. Okay, and we like those creatures. Trust me, research has demonstrated that we really need those creatures. Okay, lots of research has hit the primary literature in the last 2 decades, showing how important those creatures are to us. Okay, so anyway, prokaryotes are going to produce quite a bit of that ammonium cation. Okay. All right, so that's blood, right? That's where that's coming from. Now, also in the blood, and I'm going to go ahead and use a slightly different color here, would be the glutamine. This would be coming from arterial blood. Okay, that glutamine is going to come into our cells, okay, the periportal cells. There is in the periportal cells the mitochondria, so this is mitochondria. Those are also come equipped with glutaminase. Glutaminase is the enzyme, again, that deaminates glutamine, making glutamate. So any glutamine that's absorbed by these periportal cells is going to produce the ammonium cation through the glutaminase reaction. Okay? And again, that glutamine really doesn't come from the portal vein. It really comes from arterial blood, okay, from our other cells in our body. Now, other sources of this, okay, amino acid catabolisms, okay, this would be source number 4. As I just mentioned, amino acids can be broken down into carbon dioxide and water by these cells. Okay, so they absorb amino acids, not isoleucine, not leucine, not valine. Those are going to pass on through, but the other amino acids they will, and many of them they'll break down. They can break them down to carbon dioxide and water, or they can use them for other things, making fats, making carbohydrates, that kind of thing. In either case, right, this is going to produce ammonium. Like I showed you, serine can be deaminated, threonine can be deaminated, glycine can be deaminated. Okay, by deaminated, I mean they just remove the nitrogen and make the ammonium cation. Okay, so this would be, right, amino acid catabolism. Okay, and I'll just put deamination. Now, what can also happen in these is that alpha ketoglutarate There can also be a transamination that will make glutamate. Glutamate can undergo deamination to become, strangely, alpha-ketoglutarate. You say, that seems weird. Okay, but it happens, okay? Because you're saying, well, it went from alpha-ketoglutarate to glutamate, and then from glutamate to alpha-ketoglutarate. Why do that? Well, the reason is because for some amino acids, there's no way to deaminate them. So the only way to deal with their nitrogen is to put it onto alpha-ketoglutarate, making glutamate, and then deaminate glutamate, okay? So, for instance, tryptophan is one of those. You can't deaminate tryptophan, but you can move the amino group off of tryptophan onto alpha-ketoglutarate, making glutamate, okay? And then deaminate glutamate to alpha-ketoglutarate. This enzyme, okay, is actually a dehydrogenase. It's called glutamate dehydrogenase. I'm running out of room here. I'll draw it over here. Glutamate dehydrogenase. That enzyme is found in high concentration in the periportal cells. Okay. That will break off another amino group, or ammonium cation, NH4 plus. That will feed into this. So the last one would be 5 glutamate deamination. Okay. That is 5 sources of the ammonium cation that are going to be found in these cells. And you notice that I pointed, in every single case, I pointed to this ammonium cation. And we're going to look at what the cell is going to do with that here in a moment. Okay. Questions on that, though? Yes?
Is that thing on the left-hand corner, does that say GLU or GLN?
GLU, glutamate.
Both of those are glutamate?
Yes, this is glutamate, GLU. And this is glutamate as well. Yeah.
Okay, so why is it shown twice?
What, you mean twice here and here?
Yeah.
Just to try and move it to another portion of the slide. But there's nothing happening, no enzyme or anything like that. Yeah. Good question. Sorry about that. Other questions? Yeah.
Is this why you have essential and non-essential amino acids like tryptophan? You said that tryptophan can't be deaminated, so can it also not go through a transamination reaction to be built up?
Yeah, okay, so the question is this why you have like essential amino acids and non-essential amino acids? If tryptophan can't be deaminated, can it not be then on the other side of it be transaminated? So you would have to look at each essential amino acid. There are reasons why we can't make them, you and I can't make them. And it depends, like the synthesis of those amino acids, if you're to look at other organisms, is fairly complex that we just miss those enzymes. Some of them may be an aminotransferase, or there may be other reasons as well, okay? Like it takes 9 steps to break down that ring system. I don't know how many steps it takes to build that ring system back up. And then what enzymes are missing in you and I that couldn't do that, okay? So that would be the keys, to look at what portions of those biosynthetic pathways are just not present in you and I. But that, I mean, the idea is that yes, there are essential amino acids because we miss some enzyme to do this. Yeah. Yeah.
2 questions. The first one, so a couple slides back when you had like the high capacity cells and the high affinity slide for
Yeah.
cells, were the cream colored cells there in the middle, did they have a special?
There is, yeah. So the question is, coming all the way back to this, there is and I can't remember what the name of this is. I'm not going to talk about it, okay? But there is a different type of cell type in between them, okay? The difference is, as I remember, when I was preparing for this, and I didn't look at it this year, I thought, well, that's not significant enough to really talk about in this class. Yeah. The second question you had.
Second question, are there any pathologies where glutamine and alanine are not the major amino acids in there that you know of?
Not that I know of. Yeah. So the question was, are there any pathologies that glutamine and alanine are not the major amino acids in a person's arterial blood? And I don't know. Yeah. Other questions? Right now, fates of glutamate, okay? I want to go ahead and talk about that. Glutamate, if you start to understand what's going on here, as you look at amino acid catabolism in these cells, lots of times alpha-ketoglutarate is going to be in the acceptor of a nitrogen, right? And that alpha-ketoglutarate is going to become glutamate. So we are concentrating nitrogen either as an ammonium cation, these sources here, or onto glutamate. So what's going to happen to glutamate? Well, the first fate is the same as the fifth source of the ammonium cation. Okay, so one of these fates is to just simply deaminate it. And that makes the ammonium cation. Okay? The second fate is this, and that's to make this thing called N-acetyl glutamate. I'll use the abbreviation that's commonly used, N-acetyl glutamate. So we have glutamate here. Okay? Glutamate, it can be made from the deamination of glutamine. It can be made from other transamination reactions. Okay? That glutamate can become this thing called N-acetyl glutamate. We'll talk about the purpose of that later on. Okay? A very important purpose, but that's one of its fates. And then finally, the third fate of this would be to become aspartate. So glutamate can undergo a transamination reaction with oxaloacetate to become aspartate. Oxaloacetate is an alpha-keto acid. If it accepts an amino group from glutamate, it will become aspartate. Now, some of you are sitting there saying, that sounds an awful lot like the malate aspartate shuttle. Bingo. That's in the malate aspartate shuttle. Okay? And of course, it makes alpha-ketoglutarate. Okay? So, those are the fates of it. Now, to sum up this slide, because it's a fairly complex slide in some ways, what I have tried to show you is that all of these amino acids that have nitrogen on them, they're either going to make the ammonium cation or aspartate. Okay, there's going to be a small amount of nitrogen left on this thing called this N-acetyl glutamate, and we'll look at the purpose of that. But those are our two places where the ammonium cation are found. Okay, aspartate and the ammonium cation. Okay. Questions? So what do we do with that? What is the body and what is the periportal cell going to do with that nitrogen? And that's the urea cycle. So we need to go through the urea cycle. Okay, I'm going to skip this slide. This just shows this is the this here is the glutamate dehydrogenase reaction. If you're really wondering. Okay, all right. So we're going to do the urea cycle. This doesn't project well at all, so I won't use this at all. The urea cycle is a cycle that is split between the mitochondria, the matrix of the mitochondria, as well as the cytosol of liver cells. Okay, you do not find the full complement of enzymes through the urea cycle in any other tissue in your body except the liver. The liver is the only tissue that can carry out the urea cycle in totality. Okay, there are of course enzymes from the urea cycle in other tissues, but not all of them that are needed. Okay, so we will start our efforts to understand the urea cycle in the mitochondria. Okay, so let's go here. We have done essentially all of this. I'm going to go ahead and scratch all this off. Okay, we don't need to understand that because that's everything that I just did. All right, where are all these things coming from? We have traced how nitrogen is sitting on glutamate. We have traced sources of the ammonium cation. Okay, we did on our last slide. We looked at deamination of glutamate to make alpha-ketoglutarate. Okay, and transamination. And we just also talked about how that, okay, glutamate through transamination can become aspartate. So in our last slide, I kind of summed that whole slide up to say that, oh yeah, all the nitrogen from all amino acids is sitting on the ammonium cation and aspartate. We're going to watch this nitrogen and this nitrogen, how they're going to be put on urea in the urea cycle. Okay. And the sources of that those nitrogen are all the amino acids that have been catabolized in our cells. Okay. So the first reaction. Let's zoom in here a little bit. Catalyzed by the key regulatory step of the pathway called CPS1. CPS1 is easier to say and easier to spell than carbamoyl phosphate synthetase. Okay, CPS1. It is going to take that ammonium cation and bicarbonate, okay, source of carbon, and it's going to make carbamoyl phosphate. There are 2 total ATP that are needed to do this. Okay, it uses ATP actually twice. Hydrolyzes 2 of them. Okay. And that makes carbamoyl phosphate. Okay. And of course our nitrogen from the ammonium cation is sitting on that molecule. Now, next step. Okay, that's CPS1. We're going to skip this slide. That just gives you the details of what CPS1 does. You can look at it on your own time. I'm not going to hold you accountable for it. Okay? I list the names of these enzymes over here because they're not fun to spell, and they're not fun to write out, and they're not fun to say. Okay, but I'm going to go ahead and list them off over here. So step number 1, okay, we've got now carbamoyl phosphate. This is a cycle, remember, so it's just like the citric acid cycle is going to circle all the way around. Okay, this first step is going to be this. It's catalyzed by this enzyme, this guy, ornithine transcarbamylase. Fun to say, fun to spell. Ornithine transcarbamylase. Ornithine transcarbamylase is going to take carbamoyl phosphate, which was just made. Here's our nitrogen. I'm going to just keep highlighting that nitrogen that came from the ammonium cation. It's going to take that carbamoyl phosphate and ornithine, this guy right here, and it's going to make citrulline. And here's our ammonium. Okay? If you're really curious about ornithine, ornithine is essentially lysine minus 1 carbon. Okay, lysine side chain has 4 carbons in an ammonium group. Ornithine has 3. It is an amino acid. It's not used for protein synthesis, though. Okay. That occurs in the matrix of the mitochondria. The second step of the cycle is catalyzed by this enzyme, even more fun to say and spell, argininosuccinate synthetase. Argininosuccinate. Doesn't really roll off the tongue. Okay? But argininosuccinate synthetase is going to make, oddly enough, argininosuccinate. Okay? Now, how's it going to do that? Let's go ahead and focus in here. The citrulline that was just produced by ornithine transcarbamylase is going to be combined. It's a 2-step process, okay? It's actually more than 2 steps, but 2A, it's going to be combined with ATP, okay? This ATP is going to split off pyrophosphate. This is going to account for another 2 ATP equivalents. Okay. Similar math that we used for the production of acyl-CoA. Okay. But that's going to make this adenylated citrulline molecule, an intermediate, that then is going to be combined with aspartate. Now I'm going to circle that nitrogen on aspartate. Aspartate, remember, is the other place where the nitrogens have been concentrated. They were concentrated in an ammonium cation. Those were put on carbamoyl phosphate. Carbamoyl phosphate was then used to make citrulline. Citrulline is now being combined with aspartate. Aspartate captured a lot of those nitrogens, and that's going to make argininosuccinate. You do not have to memorize the structure of argininosuccinate, though you probably could, and it wouldn't be too bad. You have to know the structure of arginine and succinate and put them together. Not that hard. Okay, but let me circle these. Here's our nitrogen, and here's another nitrogen, okay, that have come from other amino acids catabolism. Now, before I go on, are there any questions? That's 3 steps: CPS1, ornithine transcarbamylase, and argininosuccinate synthetase. The only one of these that plays a role in the regulation of the urea cycle is that first one, CPS1. Okay. It's irreversible. All right, now we have arrived there, so I'm going to skip this slide. That's more stuff that you can do on your own time. And we're going to look at our last 2 enzymes here. The first one, argininosuccinase. Okay. Argininosuccinase. Okay, so here's where we arrived, argininosuccinate with our nitrogens. Okay. That argininosuccinase is going to break off fumarate from this and make arginine, the amino acid arginine, which has 4 nitrogens on it. Okay? That arginine has 2 of the nitrogens that came from other amino acids. Okay? And that's step number 3 here. Now the last step, come back out here, catalyzed by an enzyme called arginase. And arginase, number 4 here, is going to complete the cycle. It's going to make ornithine. And to make ornithine, it's going to split off urea. Okay, so this step here splits off urea, makes ornithine. That urea has the nitrogens that came from either aspartate or the ammonium cation, which I tried to labor to tell you where those all came from. Okay. Urea then will be excreted, obviously, in our urine, and that is the safe way to carry nitrogen around in our body. That and glutamine and alanine, or other amino acids. Okay. And that's the urea cycle. Okay. Ornithine will then move back into the matrix of the mitochondria, and the ornithine transcarbamylase will start the whole cycle again. You'll keep feeding the cycle with carbamoyl phosphate and aspartate, which is our sources of nitrogen. Okay. Question, yes?
Are ornithine and citrulline able to freely pass through the mitochondrial matrix?
Yeah, there's transporters, but they're direct transporters. All right. So the question is, what about, like, when you look at ornithine and citrulline, are they able to pass through those membranes? They have to be transported, but they're direct. They're, we looked at this, right? Aspartate coming out of here. I didn't really mention this, but aspartate comes out of here. The malate aspartate shuttle will be part of that, right? Moving aspartate out, there will be a glutamate that moves in. So. Question?
Am I completely off base here, or was fumarate, that was what was stuck in complex 2, right? The citric acid cycle, was that what that's
Not fumarate, FADH. Yeah, fumarate was the product of succinate dehydrogenase. Yeah, okay. But it was diffusible, it left. Yeah, now that fumarate can then feed into the last couple of steps of the citric acid cycle. Other questions? Okay. right, let's look at regulation of this. I ran out of time, so I can't ask you questions. I'm sorry. Okay, so urea cycle is regulation here. Let's look at this quickly. How much time? Yeah, we got enough time to do this. Okay, so the regulation of the urea cycle comes down to this molecule N-acetylglutamate. So if you remember, N-acetylglutamate was one of the fates, if I go back several slides, wow, a lot of slides. There we go. One of the fates of glutamate was to become N-acetylglutamate. It was either that or deaminate it or make aspartate from it. We've seen what happens when we make aspartate out of it. Now we need to think about N-acetylglutamate. Okay? N-acetylglutamate is going to activate CPS1. CPS1 carries out the first step of the citric acid cycle, essentially the production of carbamoyl phosphate. It's the rate limiting step of that. Okay, feeds the cycle. Now this is really fascinating. Carbamoyl phosphate synthetase, or CPS1, if it does not have an N-acetylglutamate, the enzyme is completely dead. It's one of the very few enzymes that we find that is completely dead without its activator. Most of them, remember I talked about at the very beginning of the semester, when we talk about inhibition, usually we're talking about a dimmer switch. This is truly an off switch. If it's not there, it's off. It's not even functioning. Okay, so it is an obligate activator. It has to be there. So N-acetylglutamate is very important. Now, the enzyme that makes N-acetylglutamate is this guy over here, N-acetylglutamate synthase. It will take that glutamate and it will take acetyl-CoA, combine them to make this N-acetylglutamate. Okay, it's just a glutamate site or amino acid with an acetyl group attached to its alpha amino group, and that's all it is. Okay. Now that enzyme is activated by arginine. If arginine concentrations are going up in the cell, that would be an indication that a portion of the citric acid cycle is starting to run. Okay. That will feed forward and activate CPS1, okay, and CPS1 will then start to make carbamoyl phosphate and start to really churn the urea cycle over. Okay. All that's happening at a really high level in the periportal cell. Like I said, the periportal cell has a very large capacity to absorb ammonium cations and make urea. Okay, if it doesn't do that, ammonium cations will get into our systemic blood and kill us. Not nice. So thank goodness for the periportal cells. Okay? All right, now, special topics. No time to do special topics. So we're not gonna do that. Okay. The perivenous cell, let me just mention this, and then I'll come back and review things on Friday, which will be our last day of content. Periportal cell, high capacity for ammonium cations. Perivenous cell has a high affinity for them. Okay? And any ammonium group that gets through ammonium cation that doesn't get captured by the periportal cells or cells prior to this will be absorbed by the perivenous cell. And the perivenous cell has the urea cycle in it, but it doesn't have it nearly to the capacity that the periportal cell does. Okay, the enzyme concentrations aren't nearly as high. But it does have this enzyme in it. It's called glutamine synthetase. Okay? And glutamine synthetase is going to take a glutamate. Okay, it requires ATP to do this. It'll make glutamyl phosphate with that. It's a two-step process, and then it will take an ammonium cation and add it to the glutamate. Okay? That will make glutamine. So that's what you're seeing over here. Anything that makes it through the periportal cell be absorbed by these cells. Okay, glutamate will be converted to glutamine by glutamine synthetase. This requires ATP. And then glutamine will be put back into the bloodstream, and that will hit the systemic system. Okay. And that's all we're going to say about the perivenous cell. Urea is going on, but not nearly to the capacity. Okay. Whew. Some of you are saying, wow, that was metabolism. Lots of enzymes. Okay, so yeah, it was fast. So Friday's our last day, so we'll try and capture some more stuff on amino acid metabolism on Friday, okay? We certainly won't finish it all, okay? All right. By the way, the problem set, you're ready to do the problem set now. We've covered everything for that problem set. What's that?
The study goes that you